Section 6.6, we get into rational and irrational numbers. And this is a topic that is something we've talked about first semester in first chapter, but we've also ran into rational numbers and then earlier in this chapter, irrational numbers. So let's redefine them. Rational numbers, if you remember, are any numbers that can be written in fraction form a over b, where a and b are integers and b doesn't equal 0, because obviously we can't have a 0 in the denominator. Irrational numbers were numbers that can't be written a over b. So common ones here would be like the square root of 5, not perfect radicals, pi, and so on. We can actually even take a look at a different way of defining them, and that is to look at the decimal version of it. If we're looking at a decimal for rational numbers, your decimals are either going to terminate, which means end, like 0.65, it ends, or it repeats. So like 3.282828. Whereas irrational, if you're looking at the decimal, they are non-terminating, non-repeating. So pi would be an example. Or if I had 3.147265, ... the ... dots means that it continues, but there's no distinguished pattern. So the first part of section 6.6 just has you go through and identify. And you can either look at it in terms of fractions or in terms of a decimal definition. But here, if I have 3.5 because the decimal ends, this is rational. Square root of 36 is a perfect square root. It gives you 6, so this is rational. 2 pi would be irrational. The square root of 5 over 3, if it is an imperfect radical, it is automatically going to be irrational. If you want to plug that into a calculator, you certainly can, but it would definitely be non-repeating, non-terminating. Problem number 5, automatically, if it's repeating, it's rational. 6, there's no distinguished pattern, so it's irrational. 7 would be rational. 8 would be irrational. Be careful not to automatically assume that something with pi is irrational, because if this had been 3 pi over 2 pi and the pi's could have canceled, this would have ended up a rational number. The next part of the assignment has you looking at rational numbers, and they're going to give you a fraction and you have to change it to a decimal. You've been doing this since elementary. Pull out a calculator. 3 divided by 8, 0.375. 3 divided by 11, 0.27 repeating. Please use the repeating bar when writing a decimal. So this part should not be hard. You guys have done that for several years. The last part of the assignment has you going the other way. They want you to take a decimal and write it as a common fraction. Common fraction means a over b. So improper sometimes, maybe, but you'll never have a mixed number. So if I have 13.2, this is 13 2/10, which is 13 1/5. So write it as a common fraction would be making this improper and making this 66/5. 0.8 would be 8 over 100, and then reducing by 25, or reducing by 4, excuse me. And 12, 3 and 1 over 1,000 would give you 3,001 over 1,000. When we get into repeating, changing repeatings to fractions are not that straightforward, because you can't just simply put 2 over 10 or 54 over 100. What we're going to do is we're going to create 2 mini equations. And as long as your repeater is right after the decimal, that is going to be our x equation. We're going to let that be x is equal to 2 repeating. Then what we're going to do is, because there's only one digit that's being repeated, I'm going to multiply both sides by 10. And I'm going to put it above because that is our second equation. And if you take 0.2 repeating and multiply it by 10, all it does is just move that decimal over. And so now this is 2.2 repeating. What we're going to do with these equations is now subtract them. And when we subtract them, we end up with 9x is equal to this repeating part cancels, and that's the whole point of this. Creating two equivalent equations that when we put them together, we are canceling the repeating, and then when we solve, we come up with our fraction, 2/9. So that's really what we're doing, is looking to create two equations that are equivalent that we can put together, cancel the repeating, and give us an equation that we can solve to get our fraction. So on 14, my repeating part is right after the decimal. So I am going to let that be equal to 0.54 repeating. I'm going to have to take both sides by 100 so I can get the decimal moved 2 places. Subtract, 99x is equal to 54. That repeating cancels. Divide by 99 and then reduce. I can reduce by 9 here and get 6/11. And you can always check. Pull out the calculator, take 6 divided by 11, always check. If you have a whole number out front of it, you can still, as long as that repeating is right after the decimal, you can still let that be 3.06 as your x. Multiply by 100 because we have 2 decimal places. Subtract. The repeating is going to cancel. Don't forget that you have this whole number 3 here. Divide by 99. X is going to be reduced by 3, 101 over 33. Here is where this very last one is a what if. What if the repeating does not happen right after the decimal? Then, yes, this is going to be equal to x, but we're not going to use this equation to mesh together. Okay? Our first equation is multiplying to get that decimal right in front of the repeating. So my first equation is going to be 100x is equal to 6.5 repeating. I want to get that decimal right in front of the repeating. Then I can multiply both sides again by 10 to then move that over one more place. And so this would give me 900x is equal to 59. And then x is going to be equal to 59 over 900. So trying to find some shortcuts, sometimes you can recognize a pattern with the 9, 99s, and so on. But if the repeating does not happen right after the decimal, then you have to get that decimal there. And your denominator could be 990. It just depends. 9,000. Just depends on where your decimal is.